Welcome everyone. This is actually it was mentioned as the second Google meetup, but it's actually the third one that we have here at Google. The first one was April of last year, and I would like to introduce you to Thomas Wilde. He's been a pusher since the last two ones, at least. He's been pretty much the organizer externally, and we were very happy to have all of you here at Google. And I think that's all I have to say.
Okay.
Thank you.
So welcome to Go from A to C. And first of all, I'd like to thank Sydney, publicly, and Google for providing us with this awesome space today. Round of applause, please. It's really a great opportunity for me to be standing in front of you today. It's cool to see so many attendants coming to the Go meetup. And so I think the bases are covered. You know where the sandwiches are, where the beer is, all the beverages. And so today's agenda is quite simple. We have 4 speakers. First, I'll introduce you to Go, the programming language, the concepts, the history, a little bit of everything, so you can get started with, typical Hello World program, all of that. Second goes Matt Proud, Google's own, with unit testing. He'll show us how to black box test all kinds of different Go applications. After that, we'll learn how Go excels in the web with REST APIs and so forth with Stefan. And last but not least, Martinez is going to show us his very secret project of how he ported Go to a new OS. Okay, so without much further ado, I'll just jump right in. It doesn't work, sorry. Okay, so not too long ago, in 2007, these 3 people, they met. They were working at the same company. You can guess which company that is. And they basically decided, hey, the languages that exist today are not enough. We want something more simple. So to give you a quick introduction of who these people are, on the left, we have Robert Griezmer. He worked on a JVM called Hotspot, also on another virtual machine called V8. That's a JavaScript engine. In the middle, that's Rob Pike. He worked at Bell Labs. He co-invented a coding scheme for Unicode called UTF-8, and also works actively on Plan 9, which is a Unix successor, the official Unix successor, if there was one. And the guy to the right, that's Ken Thompson. So he co-invented a lot of stuff, and himself, he also did a lot of work on himself. One of the things is the C programming language he designed together with Dennis Ritchie. He's also one of the main people behind Unix. So basically they realized we have 2 kinds of languages in the market today. The ones that are fast to write and the ones that are fast to execute. On one side we have Ruby, PHP, Python, Perl, and so forth. On the other side we have C, C++, to some extent Java, C#, and so on. They require a lot of boilerplate, a lot of complicated writing to get a speedy program. So why can't we unite these both concepts and additionally make it so that the compiler is also speedy, fast? That it shouldn't take forever to compile a program, because at this very company they had C++ programs that were compiling in hours. They were actually, they couldn't know if the program was going to work or not until it was compiled. And so they had to press the button, leave 4 hours, come back later, and it would still be running. So that sucked. So that was the target as well. So they made a couple of observations. The first of which is that manual memory management, as you know it from C or C++, it really sucks. We humans suck at manual memory management. It's a security risk. It's an old story that you get this super old OpenSSL library or whatever it is that has some buffer overflow that leads to remote code execution, or et cetera, et cetera. So really, memory management is nothing for the hands of humans. Then secondly, people, they like static typing. If you look at the web right now, JavaScript is transitioning to TypeScript. Angular 2.0 will be written in TypeScript. A lot of other languages are gaining type hinting, or where you write the type annotation before the variable. PHP 7, for example, is coming out with static type hints for scalar types, which is new, etc., etc. So let's make a language that is typed, has a static type system that we can check at compile time to remove a whole class of errors from the runtime. Thirdly, and this may be a little bit controversial, but inheritance doesn't scale. So I guess it was the 80s when inheritance as a development model boomed, when everyone thought classes and extends and etc. was their way to program. There was no other way. So over the years, we've learned that inheritance trees tend to grow exponentially. Like in the end, you have this big inheritance tree with tightly coupled things going around further and back, and it's not really maintainable anymore. So let's try to solve that in some intelligent way, with something that we already have. Another point is that languages, programming languages, they tend to become products. In the long run, when a language has a little bit of success in the world, they tend to become this thing that gains features with every new release. Like, I don't know, Java gained those lambda expressions, or C# gained link, and with every new version of your language, you get more and more features. And so everything becomes a little bit more complicated, because now you can't parse your language linearly. So you have C#, for example, which has this Tomita-style GLR parser, which is O(n) cubed, which is just, it's huge. It's a huge trade-off for the parser, for the compiler. It makes compilers big and difficult to maintain. So let's keep it small. Let's make Go a language that we design today in such a way that it can hold for at least a couple of years. So, and one last observation, the obvious, is that CPU cores today are a concept. 10 years ago, we had just one core on each CPU. Today, we have, I don't know, in your commodity laptop, 8, 12 maybe. And it's expected that we're going to have a lot more, like hundreds of them. So let's make use of that. Let's parallelize our programs. Instead of gaining linear speed, let's make them concurrent, parallel. So they designed the Go programming language. First of all, it's compiled. That means there's no interpreter, not like Python, PHP. There's no virtual machine like in Java, JavaScript. It compiles to, I think, 11 different OSs, combinations together with architectures. So you can have it on Mac, Windows, Linux. You basically write one program, you just compile it for whatever you need it. Second point, it's statically typed. That's what we discussed just right now. It's types are enforced by the compiler. And you have to play by the rules of the compiler, which is much smarter than you. Third, it's garbage collected. I guess this was kind of a decision, because there's also other ways to administrate memory automatically, like reference counting, etc. But garbage collection seemed like a fair trade-off. And it's worked quite well. So there's going to be no inheritance, as you know it. There's going to be embedding, which is a different concept. It has to do more with composition. You know how Java devs and C# devs are doing dependency injection? It's more or less that, just in the language, not like an additional feature. Then it has to have structure, and this is not a problem with modern languages, but if you have ever written C, it sucks, because for every header file you have to declare some kind of a constant that you check for the next time you import it, so you don't import it twice. So basically, if you forget to do that, you'll end up either in an infinite loop, or you import your library like 1,000 times, which sucks. So it's got to be packaged, structured, by default. Next, there has to be concurrency built in, and it has to be easy. Using pthread. Has anybody ever used pthread here, the library? Yeah, it sucks, right? It's really difficult to use. I mean, even if you actually grasp it and you understand it, it's still kind of this heavy thing that you have to carry around and work with, where you have to distribute your work around threads and managing this stack local storage thingy. It sucks. So let's make that easy. And overall, let's keep the design of Go simple, small, and speedy. So in this talk, we're going to be seeing a lot of types, and I assume some of you guys work with dynamically typed languages. So I'm just going to explain the basics of that to you. At the very top on this slide, we have a function definition called add, and it takes 2 integers, and it returns an integer. It just sums them together. Wow. So types in Go are written after the identifier. That's contrary to most programming languages you might know from the C family, like Java, C#, etc. And the reason is actually quite simple. You can read type signatures from left to right. Below, I have some C code. That's a valid C declaration, and it means declare X as function returning pointer to array of pointer to function returning character, whatever. I got that from a web page dedicated to this. You can actually type in a signature and it will tell you what it means. So if you have a need for a web page that does this, you're basically screwed up, right? So in Go, that reads like you can see at the bottom. It's X, and you see it's a function, then it returns pointer to slice of function to bytes, whatever. So you can define your own types in this language. We're gonna look at what types there are by default in Go in a couple of slides, but for now, just know that whenever you write type, then a name, and another type name, you basically are declaring your own type based on that other one. A little more interesting type signature would be the one you see in the middle, which is a struct. C programmers know structs. For the rest, it's basically like a class. Those are the properties of it, and they have types. I mean, an animal has a name, that's a string. Wow. Speed is miles per hour. That's the thing we declare at the top. And then it has 2 parents. Well, it's a safe assumption to make 2 parents. And then more interestingly, we have interfaces in Go. And this is kind of that thing that makes Go work in the way it does. We're going to see a lot more about interfaces later on. We have this converter interface that says anything that has a method convert, which takes a byte slice. A slice is like an array. We'll see that. And returns a byte. That's a converter. So we have predefined types built into the language. At the very top, you have the typical Boolean, which can take 2 values, true and false. Then you have bytes, runes, which are basically 8 bits and 16 bits, respectively. Strings, which have a length that's new for C developers. Error, which is a built-in interface. And we're going to see how it's defined later on and what it's used for, because error is something you're going to see a lot in Go code. Then you have the 2 types of floats. So that's real numbers, floating point types, 32-bit wide, 64. Then you have architecture-dependent integers, int, uint, and unit pointer, which is a bit special. And then the architecture-independent inner types. And last but not least, complex, but I've never used it personally, so I couldn't tell you how well that works. And there's also these composite types. So just assume that X, Y, C, Q are other types. So composite means that the type itself is defined in terms of other types. The most simple case is the one at the very top. It's a pointer to X. So whenever you see a little asterisk and a type name, you know that's a pointer to something. Again, the asterisk is at the beginning of the type name, not at the end, like in C. Then you have the slice of X, which is like an array, but it has no defined length. It can grow. That's the second definition you can see there. The third one is an array. an actual array, which has a fixed length. It doesn't grow. It's just exactly that, what it is. A map is a hash table. It's built into the language. So you don't have to worry about implementing your own, although you can if you need one. Sure, go ahead. Then there's this ChanX, that's channel. This is used for concurrency, and we're going to see how. Just leave it at that for the moment. Then a struct, we saw a struct earlier, like a class. Functions, of course, are also typable, and they are composite because they take different arguments of different types and they return several arguments. And that's something Go has made a little bit special. You can return more than one result from a function. 2, 3, doesn't matter. And then lastly, the interface, which most definition we'll see later. So maps and slices are really not that difficult. It's a slice is what you would call a list in Java, or a collection in C#, or a dictionary in Python, or an array in PHP. I don't know. It's basically gross. You can just append stuff to it, and it just works. You don't have to worry about how big it is, allocating memory, whatever. Then maps, same thing. Hash tables. They map from one type to another. In this very simple example, we're mapping from strings to Boolean. So we can say, yeah, map yes equals true, and map no equals false. You can basically use almost any kind of type for the key, except maybe functions, which would be a bit awkward, because how do you compare functions? It's weird, but whatever. So now comes the more interesting thing. Any name type, so any type that basically you define and is not composite, or no, that's actually the wrong way to say it. Any type that you defined can have methods attached to it. So it doesn't matter if it's an integer-based type or a function, it can have methods. And the way we attach methods to types is this weird notation you can see right below the person definition. So you can see that person has a first name, a last name, which both are strings, and an age, which is an init. And then we define full name, which is a method of person. And the receiver is this first argument, which is kind of in the middle between the func keyword and the function name, full name. And that's kind of what you can think of as this in Java, or in any other language, maybe. It's the this parameter. So we're returning P first name plus space plus last name. And P is this, so the current object. A very simple example is that we instantiate a new person, which has first name Ehrlich, last name Bachmann, age 29, and we just take its full name, assign it to this variable called n, and then we print it. The print thing, I'll explain later why that notation goes like that. Also, the short variable names are customary in Go. So we tend not to have these huge Java-esque variable names where the thing is kind of described in itself. We tend to use short identifiers, except for functions. Functions should be, good practice. So let's see the Hello World program. Go is organized in packages. And there's one special package, which is called main. The main package is the entry point of a program. It has a function main defined in it, and as you might expect, that's where it all starts. In this case, we're importing another package called font. We're using font, which has an exported function called println, to echo hello world to the console. Nothing out of this world, so let's move on. If anybody has been paying attention, you might have seen that the capitalization of my names are a bit weird, if you're a Javaist or whatever. That's because in Go, public identifiers are identified by an uppercase letter at the beginning. So whenever you write a big F, a big H, whatever, at the beginning and then the name, that's exported. Other packages can see it. Equally for structs, other packages can access the members of the structs. If you write them in lowercase, nobody can see them. They're private. As we have no inheritance, there is no need for protected. So let's write a package, a simple one with one type, one method. The type we're going to define is session identifier, and it's going to be a string-based one. Then we're going to define the session itself, which has an ID, username, and it expires at some point in the future. Again, we imported another package from the standard library called time, and we're going to say that expires is of type time. That represents a time. Well, then we have one function called init session. It takes a session identifier, it returns a session. However, it is implemented is not relevant. It's just to get you an idea of how a package is written. So you can see that the three identifiers we defined, so session identifier, session, and init session, all have a capital letter at the beginning. That means other packages can see them. They're public. So now let's assume I push this to GitHub, right? My session package. I found it cool. I decided I wanted to share it with the world, so I put it on GitHub. And now another user who may have stumbled upon my code can say, hey, cool, let's try it out. So he goes to his console and he just writes go get github.com/my-username/the project, which is called session in this example. And he can just use it. You can see in the import statement that we're actually writing out the entire URL, excepting for the scheme. So github.com/thwd/session. And the name of that package in my scope is session. So whenever I want to access init session, I'm going to write session dot whatever. So in this example, I have this handle HTTP request function, which let's assume is handling some kind of web application. So first, on the first line, I'm going to take the cookie value, session ID. And that underscore you see there, it's omitting the second return value of cookie, which is an error. So if the cookie doesn't exist, I get an error. But I'm just going to assume it does, and I get an empty string if it doesn't. Then I'm going to use my package session.init session. I'm going to pass the cookie value, which would be the session ID. And then I'm getting the session back, right? I'm just going to print out the username to the web browser. That's a very simple contrived example. So one thing about Go that not many people like or they get confused about. We have pointers. And a lot of people think that pointers in Go are just as bad as they are in C or just as complicated. And they really get scared when they hear the name pointer because they heard it in college and it was so painful and whatever. So Go is normally passed by value. Everything is passed by value. So it means that whenever you give an argument to a function, it gets a copy of that argument, not the argument itself. Java is quite on the contrary. Normally, when you pass an object, the function or the method receiving the object gets a reference to it, and it can mutate it and call methods and whatever, and can alter its state. That's not the case in Go. It's passed by value. So the way we take a pointer to something is this notation. We define P as ampersand of S, taking the address of. That's what ampersand means. So if S was of type string, then P is going to be of type pointer to string, which is this asterisk. And these pointers work exactly like in C, except there's no pointer arithmetic. Why? Because we want to be memory safe. If we had this, we could basically access any part of memory and just do whatever we want with it, and that wouldn't guarantee anything. So we decided against it. There's no casting between pointer types like in C. So you can't just say, oh yeah, that's a pointer to init. Let's interpret it as a pointer to a float. No, you can't do that. You have to convert. Nil, which is what you know as null, is well defined. So there's never that question if null is going to be equal to 0, or if it's some weird macro defined somewhere, or a compiler extension, or defined in some other roundabout way. It's just in the language, it's nil. It's always the same. And there's no arrow operator. So Doesn't matter if you're accessing a field, for example, on a struct that is referenced by pointer or by value, you can just use the dot. And the net result of all this is that we have a memory safe language.
Go back to the other.
Yeah, sure.
One more. You already defined that session is a variable ready to use because we imported your other projects.
Exactly.
It's a bit confusing when you're reading a big project with you have these magic variables around. Do you have any way to?
Yes, you can overwrite them. If you have the need to like change the name, you can just write it in front of the import path. The import path is the string itself, where you see github.com/th blah blah. You can just write a name there. Then you can import it as S or S0, S1, whatever. Yeah, you can change the name. You can even import it without having a name for it by putting an underscore in front of it. Or you can import it so that everything declared in that package is now part of your package with a dot. But that's kind of an advanced use case. I wouldn't cover that in this introduction. Sure. But yeah, you can change the name. By the way, if anybody has any question or doubts at any time of the talk, just interrupt me, please. Ask your question. There are no stupid questions.
So let's suppose you push a new change to GitHub to your project. So does GoGet support some kind of versioning? Or?
Yes. So since Go 1.5, we have this vendor experiment thingy where you can actually version your libraries and the whole kind of version management. The thing is, the problem isn't really solved in the sense that it has no solution in the end. It's always going to be a bit quirky if you import a library which imports a library that you already import but with another version, and that gets confusing real quick, and you can have different versions of the same library installed, whatever. So they try to avoid that at all costs, but we kind of gave up because people demanded this feature for a long time. So it's now part of the language as of 1.5, which is the later version. Yeah. Okay. Yeah, we have package unsafe for stupid things, like casting pointers, reinterpret, and all that stuff. If you're writing like a performance critical section of some big program and the bottleneck is really there, you can use unsafe to hack around it and manipulate data just like in C. You have all the power that you have in C just by using this package. It's a kind of a special package in that sense. I'm not going to show you how to use it, not today. So polymorphism might be on your mind by now. So I said there was no subtyping, no inheritance, right? So how do we deal with that? We have these interfaces. So if you're doing OOP today, you're probably using interfaces as well. The nice thing about it is that any inheritance tree can implement this interface. It doesn't really matter where it comes from or how it's defined, as long as it has the methods to fulfill an interface. And in Java, in C#, etc., you would write my class implements the interface, right? In Go, you don't. You just implement it. You just make the methods, and then it's automatically there. You can use it. So if I define this type database adapter, which is an interface that has 3 methods, one called connect that takes in a config and returns an error, one called execute, taking in a query and returning a result, and one called close. I can just implement these methods in any type I want, and I can automatically use them as a database adapter. We're actually going to do this in the next slide. Error is the one built-in interface. It has one method called error, and it returns a string. So in Go, there's no throw statement. You don't throw things around. You return a second result, or a third one, if you already returning 2, which is an error. And then your caller has the responsibility to check for it. Normally, it's nil. That would mean everything was OK. If it's not, something failed, and you have to act on it, right? So it kind of forces you to actually deal with exceptions or with errors. Because what we have observed a lot is that in the OOP world, people tend to just write this global exception handler at the very top of the stack, just let everything else throw up. And whenever that global exception handler catches something, it will, you know, write like a general message like, yeah, I think something bad happened, look at the stack trace. So in Go, you can actually handle the error in context. You're basically forced to. You have to say, okay, what happens if I'm getting an error connecting to this HTTP endpoint? And then you could decide on a smart message that would actually help the person observing the error to fix it quickly. So that's error. So as I said, interface implementation is implicit. That means you don't have to write implement blah. It just does. So let's implement the error interface. At the very top, we have this connection error type, which is an empty struct. What's an empty struct? It's basically a type with 0. It doesn't cost you anything in memory. You don't have to ever allocate it or define it. It's just, it exists only on a language basis, basically. And it has this error method, which returns a string. And I mean, okay, this string is not very contextual or good or whatever, but you get the point. It returns an error. And then we implement database adapter. And in this example, we are implementing database adapter through a map. So a hash table in memory. A hash table from queries to results, which kind of makes sense because we have this execute method, which takes in a query and has to return a result. So we can do it by just mapping it. In the connect method, basically nothing bad can happen if you're in memory, right? So there's no connection to memory. But there's a special little thingy there. I'm checking A, which is the receiver, which is more or less equal to this, to be nil. That doesn't make sense in a lot of languages. In Go it does, because the receiver can actually be nil. You can instantiate a type and say its value is nil and just call methods on it. There's basically like static methods if you want. So I have to check for it. If it's nil, I'm just going to return this connection error that I defined. And close makes no sense in this context, so I just implemented it, but I left it empty. And now I have a perfectly valid database adapter that I can use everywhere where a database adapter is expected without implementing explicitly anything. Also, for the functional fans among you, we have lambdas with lexical scoping, like in JavaScript and whatever. They're closures. And I wrote together a small example for you just to demonstrate that it actually works. And so this function, quote of the day, takes a function as argument, so it's a higher order function. And it will call its argument with the string testing shows the presence, not the absence of bugs. Then, outside of that scope, I defined a variable called A, which has the value Edgar Dijkstra, which is a computer scientist, if you don't know. And P, which you can see is now a lambda. That's exactly what quote of the day expects, a function that takes a string, and will just print it. And additionally, it will print A, which is in its lexical scope. It's not defined as an argument or part of its definition or whatever. It's just in its lexical scope. So it's a closure over A. And we call it, and it works. For JavaScripters, this is like the coolest feature because they're very used to do this. For the rest of you, man, look into it. It's actually kind of fun. So now I told you at the beginning that concurrency and parallelism was built in, right? So that's implemented through this concept of Go routines. Go routines are like very lightweight threads or fibers for the Rubyists, Pythonists, I think. And we can start one of these Go routines by just writing Go in front of a function call. And that function call won't take place in this thread. It will just be scheduled and will run parallelly somewhere. Normally just write them, but it could happen in like a couple of milliseconds or whatever. So here I have this function execute job, which takes a job ID, which is an int. And it takes a long time to complete this job, right? It's going to be spinning for, I don't know, 5 minutes or something. So I have this job ID, 768, and I'm just going to call go execute job with another ID. I don't know why I did that, sorry. But whatever, it executes parallelly. So it's spinning in the background. I'm just going to print, OK, job is now running. And whatever happens after that, we don't care. This is cool, but it has the limitation that we never know when the job is finished, right? And we actually want to know that because we might want to clean up or notify or send an email. So we're going to use channels to do that. Channels is that weird type with the chan prefix that we saw at the beginning. So this is how it would look if we just use a channel that basically notifies us whenever that concurrent job is done. So execute job has changed from taking just one integer to an integer and a chan of Boolean, just because whatever. Doesn't matter what type it is, because we're only going to use it to notify, not to actually transmit any information. So additionally to this job ID, which I already superfluously defined in the last slide, and I did it again in this slide, we're going to define done, which is going to be a channel of bools. And we use this make function. Make is good to create slices, maps, or channels. Then we're going to execute this job and pass it this channel. So the job knows about the channel. Then we're just going to print, just like before, the job is now running. And then we have this arrow thingy before the done. That's basically wait on a channel. So the program is now blocked right there where the arrow with the done thing is. And it won't continue until someone writes to that channel. So it's reading, it's pulling out a value, but it won't continue until it has something. And luckily, our execute job function over there, which is running in another Go routine, whenever it's finished, it's going to write the value true to this channel. So as soon as it writes it, it unblocks the other Go routine. And that can continue. And the net result is that we can print the message, job is now finished, whenever the job is done. So that's the basics of channels. Now, they seem like a very simple tool, but you can actually do very powerful things with them. A little bit more advanced kind of thing is the worker pattern, which is basically you spawn these Go routines, which are waiting for works on channels, and they do them, and they notify the caller. And we can actually run this example in the browser because Go compiles to Nickel, and Nickel is an architecture that runs here, so you just run it. And what we see is that we have 8 workers, which are spawned in the first for loop. And they are giving access to the channel C, which is a channel of strings. Now, in the second for loop, we're going to write words, just strings, to that channel. And on the other end of that channel will be one of these workers. It's pretty random which one it is, but we don't care. We have 8 concurrent workers that are distributed on our threads, right, on our CPU cores in the end. And they can do their work however they please. So we're just going to distribute the work to them, wait them to process them. In this example, instead of actually doing anything useful, they're just sleeping for some random thing between 0 and 3 seconds. And when we're done with all that, we're just going to close the channel to basically close all the Go routine, the worker Go routines. So they stop using any resources, and the program can exit, and we're done. Net result is this thingy that you saw over here, where you can see that the workers are not working serially. They're just kind of randomly distributing work around them. And this example would take at least, I don't know, 3 slides to implement in any other language than Go. Maybe Erlang would be possible in 1 slide. But I don't know enough Erlang, so. So, to bring this to a conclusion, here are 4 very good resources that I totally recommend you read. The first is Effective Go, which is kind of the go-to manual to write good Go code. Secondly is the standard library documentation. You will need that. You will need that. Third, the Go playground. You can just type code there in the browser and execute it. without installing any compiler or anything. So if you just want to toy around with Go, try it out, whatever, just go to the playground. And fourth, the Go tour. So if you're really interested in learning Go or learning to program, just go to the Go tour and go through it. It's a step-by-step tutorial that will teach you everything you have to know. So you're now Gophers. Congratulations. With this, I conclude my talk. Next, I think Sydney wants to say a word.
If there's any questions, we can walk with the microphone around.
Yeah, sure. If we can do a Q&A.
Hello. Yes.
Does anybody have any questions? Remember, there's no stupid question, just stupid answers. So whatever you feel you didn't understand, just ask. Was I so clear? So everybody got it. You could program now, okay?
Excellent. So we will thank you very much, Thomas. Yeah. Round of applause. Thank you. And then next we have Matt, or which one? Yes, Matt. And after Matt's talk, we'll have a quick break. You can go to the bathroom and then have a sandwich or a drink. So thank you very much, Thomas.
Yeah, sure. Hey, and about the sandwiches, please eat them. I made 70 sandwiches today, so please eat them.